Today we have Ke Wu, who will be presenting what can crypto do for decentralized mechanism design.
Thanks for the introduction and thanks you for coming. And just to mention, this talk is also for my speaking skill test. Yeah, today I'm going to talk about our recent work, what can crypto do for decentralized mechanism design? This is a joint work with our very own Javier and Elaine. Elaine is not here today. So in this work, we concentrate on transaction fee mechanism. What is transaction fee mechanism? As we know, real estate on a blockchain can be really expensive and users do want to get their transactions confirmed on the block. Often they have to compete to get their transactions confirmed on the block. So basically we can view this as an auction where the miner who mines the block acts as the auctioneer and sells the K slots in a block to the users, where this K is the size of the block. So to decide who will be confirmed, we need to run the so-called transaction fee mechanism. It decides which transactions to confirm and how much they pay and how much the miner gets. As a quick heads up, it is not necessarily the case that all payments go to the miner in transaction fee mechanism, and we'll see more examples later. For example, Bitcoin employs a simple first price auction. Let's say the block size is K, then the top K bids will be confirmed and each bid pays its own bid. All payments go to the miner. For example, if this is the mempool, which contains all the bids from the users, then the bid 9 and bid 7 will be confirmed and they each pay their own bid. All payments go to the miner. However, as we have learned from algorithmic game theory class, first price auction is not good because it incentivizes users to bid untruthfully. For example, I only need to bid 6.1 here to make me barely enough to be the top 2 bids, and I will be confirmed, and I only need to pay 6.1 rather than 7. So first price auction is not good because it encourages users to bid untruthfully. Interestingly, actually, all classical mechanisms fail for the purpose of transaction fee mechanism. Let's say, for example, second price auction, which is kind of a golden standard in classical mechanism design because it incentivizes users to bid truthfully. Why not just use second price auction? In second price auction, still we confirm the top K bids, and now each bid pays the K plus 1 bid as the price. For example, if the mempool is still like this and we still confirm the bid 9 and the bid 7, and now the price they need to pay is 6, which is the third bid in the mempool. What can go wrong here? A strategic miner can now inject a fake bid 6.9. This 6.9 is not going to be confirmed, so miner does not need to pay for the injecting this bid, but now the 2 confirmed bids has to pay 6.9 instead of 6. And miner gains more by acting maliciously like this. So in general, in classical setting, we always assume that the miner or the auctioneer is fully trusted. So we care more about the user's incentive compatibility. We care whether a user is incentivized to bid truthfully. Yes?
Are we thinking of this as the miner can place bids after seeing the user bids?
Yes.
Okay.
It can inject after seeing the mempool. So yeah, in decentralized application, however, the miner can also be incentivized to deviate, as we just saw, and they can manage to increase their revenue. That's why the classical mechanisms are not a good fit here. So we ask the question, what makes a dream transaction fee mechanism? Exactly what properties do we want? Recently, a line of work has looked into the design of a transaction fee mechanism, and most of them agree that the following 3 properties are desired. The first one is user incentive compatibility, which is the classical notion we considered in traditional auction design. It requires that a user does not want to deviate. So a user's best response is to bid truthfully. Moreover, here in transaction fee mechanism, we also care about miner incentive compatibility, also abbreviated as MIC. Here we want that the miners also are also incentivized to implement the mechanism honestly. And the last one we care is called side contract proofness, also abbreviated as CSCP. Here we want to make sure that a coalition of the miner and C users, they also do not want to deviate. So the best response for them is just to follow the protocol honestly. So the reason we care about this is that nowadays miner user coalition are actually really happening on blockchain. So middleman platforms, they can help connect miners and users, and they can split their profit using this side contract. So we do want to guarantee incentive compatibility against this miner user coalition. The first one, UIC, is the classical notion considered, and the last two properties are actually new challenges in blockchain that we care about. Yes?
When we say a user, are we thinking of a user as an entity that is interested in a single transaction, or can one user be interested in taking up multiple slots in the block?
So in this work, we concentrate on the case where user has a single transaction. So it is interested in getting one slot. Yeah. So Timur Rothgarden asked in his previous EC21 work, can we have a dream transaction fee mechanism? And in his work, he showed that Ethereum's EIP 1559 actually achieves all three properties if we assume infinite block size. However, and when we say infinite block size, we basically mean when there's no congestion, so there's no more space than demand. So we can think of it as infinite block size. However, this is not necessarily the case in real life. We do not typically have infinite block size, and congestions can happen. Unfortunately, Elaine and Hao showed in their previous SODA 23 work that if we assume finite block size, there's no non-trivial transaction fee mechanism that can satisfy all three properties. And by trivial would mean that no transactions is ever confirmed. So if you do not confirm any transactions, okay, you can satisfy all of these three properties. But we want non-trivial transaction fee mechanism. So in this work, we asked the question, okay, can crypto help circumvent this impossibility? Can we use the magical crypto to help us design a dream transaction fee mechanism we want? And we gave an affirmative answer. In this work, we considered two relaxations. The first one is MPC Assisted model. So in MPC Assisted model, now we require that the mechanism is implemented by a multi-party computation among multiple miners. So you can, if you're not familiar with multi-party computation, just think of it as a black box that guarantees the correct implementation of the functionality we want. So you may think that, okay, if with this, yes. Sorry, can you repeat
the
that?
feasibility result was applying to which model of computation?
What computation?
The previous impossibility result you mentioned, what model of computation was that?
It's in the play model where the mechanism is implemented by the miner.
Implemented by the miner. So communication can go only between the miner and the users, but not between the users.
Yes.
Okay.
You're asking about the communication model.
I'm not sure what previous model was restricting this one purpose.
So previous model, there's only one miner, and all user can just talk directly to the miner.
Okay.
And the miner decides how I want to implement this mechanism. Okay. And now we want to involve a bunch of miners.
Wait, but now you're allowing information between users as well?
No communication between users. Just we want to add communication between multiple miners, but still no communication between the users. Each user is speaking to the miners independently.
So there are several miners, and each user can talk to some miners, and miners can talk to users, but miners cannot talk to miners, and users cannot talk to users.
No, miners talk. So okay, each user can talk to multiple miners. Miners can talk to each users, and miners can communicate with each other through multi-party computation, but no communication between users. Thanks for clarification. So yeah, you may think that, okay, if I can guarantee the correct implementation of the mechanism, does it reduce this problem to classical mechanism design? Does it trivialize the problem? It turns out no. Even with the powerful multi-party computation, the feasibility and infeasibility, the boundary between the feasibility and infeasibility is still very non-trivial, and it actually still differs a lot from classical mechanism design. Because here, user and miner, they can still inject a bit into the mempool. And also we care about the incentive compatibility of the miner and miner user coalition. And this makes it differs a lot from the classical mechanism design. And the second relaxation we considered is approximate incentive compatibility. So here we say, okay, you can gain a little bit by deviating if you want, but no more than epsilon more utility than behaving honestly. So in this work, at a very high level, we basically show that yes, with these two relaxations, we can achieve feasibility of a dream transaction fee mechanism. And also, they can help us improve the miner revenue. So we can improve how much the miner gets from this auction, and we can incentivize the miner to mine the block for us. And we can also improve the social welfare. So social welfare is basically the sum of the utility of everyone involved in this auction. So it is the sum of the utility of all users and all miners. And we show that, yes, with these two relaxations, we can improve the social welfare. So more specifically in this work, we explore the feasibility landscape of the transaction fee mechanism in these four regions. We refer to the original model without the multi-party computation, where we only have one miners who implement the mechanism for us, as the plain model. So by strict IC, we mean that the strategic players cannot gain any benefit from deviating, whereas in epsilon IC, we allow them to gain epsilon more utility. So previous work by Elaine and Hao already wrote out the feasibility of strict IC in the plain model. And we show that in MPC model, we can achieve a strict incentive compatibility. So basically, we can have a dream transaction fee mechanism in the MPC model, if and only if the miner only collude with one user. Here the C is the number of users colluding with the miner. And then we show that also approximate incentive compatibility helps, yes?
There are multiple miners, so can each miner collude with one user or?
No, all the miners collude with one user, yes.
Also same user for all the miners.
Yes.
But
So we're considering a single coalition. Yes.
Actually, if you have a C coalition, or so on the left side, if you have like a C coalition, there's a miner and multiple users. Doesn't that imply that the users can talk to each other?
Yes, you can think of that, but like the communication in the communication model, each user does not have a direct channel. Each user can, so the users in the coalition talk to each other through the miners in their coalition. So you can think of them, they decide the strategy together, but through the miners. They don't have a communication channel that link to them directly. So on the right-hand side, we show that epsilon incentive, yes.
So suppose there is this is a typical case, there's only one miner in the world, there's only one user in the world, there's only one computer device. So in that case, what prevents the miner from just robbing the user or thing? I don't understand if this is in this case. There's not a multiparty communication. There's just a part. This is just miner selling things to a single user.
So if there is only one miner selling things to a single user, then still like they cannot bring more benefit by so they cannot gain more benefit comparing to honest utility. I think we'll get to that point later.
Incentivized to be honest in this situation about their utility.
I think we'll be clear on that point later, honestly. So yeah, because there would be a process that putting information on chain. One thing is on chain, everything is public available. I think, yeah, I'll keep that in mind. And when we get to that point, I'll answer this question. So epsilon incentive compatibility also brings some feasibility in the play model. However, it does not help much. In the play model, epsilon IC is feasible if and only if we assume an upper bound M on user speed distribution. So that basically means, okay, no, I know a priori upper bound M, let's say 1,000. I know that user's true value cannot exceed 1,000. Only in that case, we can design a transaction fee mechanism in the play model for epsilon IC. So that basically rules out the possibility of a universal mechanism that works for all bit distributions. And moreover, even if we're willing to assume that, okay, I know the upper bound, it's kind of a mild assumption. Even if we allow the assumption, the social welfare, the sum of the utility of all players involved in this auction, it's unscalable. Even if users' upper bound grows from 1,000 to 1 million, the social welfare basically does not grow. And finally, we show that in the MPC model, we can achieve epsilon IC if we assume an upper bound M on the user speed distribution, and we can achieve optimal social welfare. Any more question about our results slides? I understand it's yes.
What about the scenario with, so one thing is on the right-hand side, are those proof against arbitrary coalitions or?
Arbitrary coalition.
Okay, and then the other question is on the left-hand side, what if there are coalitions that are purely among users that don't involve any miners? Do those also break the protocol?
Yes. Yes.
So what is it again for social welfare be unstable?
Yeah, so basically we want to say that, okay, if I'm only, let's say if the upper bound of the user speed distribution is 1, I'm only willing to pay 1 Bitcoin for my transaction, then the social welfare intuitionally cannot exceed, let's say, the block size. However, if even by unscalable, we mean that, okay, now even if the upper bound grows to 1,000, users are willing to pay 1,000 for their transaction being confirmed, the social welfare is still something like the block size. So it does not grow as the upper bound of the bit grows. And that is what we mean by unscalable. So in the paper, we also give the constructions assuming infinite block size, and they all achieve optimal miner revenue. But I'm not going to talk about these constructions today in the talk. And we'll mainly focus on the case for finite block size. Okay, so now in the rest of the talk, we'll gradually go over our constructions. We'll start from a very simple post-trade price auction, which is a simple classical mechanism that incentivizes users to bid truthfully. And it is basically what EIP 1559 behaves as when we assume infinite block size. We'll see why it satisfies all the 3 properties, assuming infinite block size, and why it fails for finite block size. And then we will see how we can use multi-party computation to get rid of this impossibility. However, even as we mentioned, even if we have feasibility of strict incentive compatibility in the multi-party computation, we still have 2 drawbacks. The first one is that in this construction, the miner revenue is 0. Miner is getting nothing from the auction. And the second one is that it only works if C equals 1. It only works if the miner colludes with 1 user. And we'll see how we can get rid of both these 2 drawbacks by relaxing it to epsilon IC. So in this construction, which is the epsilon IC in the multi-party computation model, we can achieve positive miner revenue against arbitrary C, and we can achieve optimal social welfare. And finally, if time allows, I can briefly go over the impossibility proof of unscalable social welfare, but I will give the statement there and you'll see exactly what we mean by unscalable. Okay, so now let's see what is posted price auction. And I think here answers that, answers the question when the world only contains 1 miner and 1 user. So posted price auction, when assume infinite size, works as follows. First, the inclusion rule says that all bids are included. So what do we mean by included? Included does not mean confirmed. Included only means that, okay, now your bid information is on chain. Once your bid, the miner decides which bids I want to put it on chain. And once your bid is on chain, it's public available. Everyone can see that. So when there's only one miner and one users, the miner can of course, the miners can always choose to put that single transaction on chain, but that will also be the honest behavior. Once this bid is on chain, it's public available. If this bid was able to be confirmed in honest case, then it will still be confirmed now. Does that answer your question? So you cannot improve your utility comparing to the honest case. Okay, cool. So, and then the confirmation rule says that once from or included bid, any bid that is at least a predetermined reserve price R will be confirmed. And then the payment rule says, okay, each confirmed bid, they pay the predetermined reserve price R, and miner gets nothing here. So here in this posted price auction, all the payments are burned on the chain. Miner is getting nothing. This is what I mean at the beginning of our talk, that it is not necessarily the case that all payments go to the miner. So let's take a concrete example where the reserve price is 4. Let's say if this is the mempool in the blue, then all bids will be included in the block. And this step is implemented by the miner. So the miner chooses. And now once all bids are included in the block, all the bids that is at least the reserve price 4 will be confirmed. So we have the bids 7, 9, and 6 confirmed, and they each pay 4. The miner is getting nothing from the payment. So this is the posted price auction. Any question about the mechanism?
What's the difference between being included in a block and being confirmed in a block?
Yeah, so being included in a block, you can think of it as now your bid information is putting on a broadcast channel. Everyone can see it. So in this large block, all the bids are included, but only the blue bids are confirmed. So this 2 bid and this 1 bid, they're not confirmed and they don't need to pay anything.
So confirmed is also like the thing that the user derives value from?
Yes. Yes.
Why don't you just everything?
So if you,
the money gets zero revenue.
yes, but then now I only need to pay as a user. I only, sorry.
Oh, incentive compatibility.
Yes, I would not be, I will only be 0 instead of my true value. Yes.
Why does anybody care whether a message is included in the block or not? Like these 2 in 1, why does it matter whether they do?
So the thing is, the miner decides which bids are included in the block, right? We want to make sure that once the inclusion rule is finished, all information are publicly available and everyone can see that, okay, this 796 bids, they are supposed to be confirmed. So I would say the miner, yes, the miner can choose not to include this 2 bid and this 1 bid, but it's the miner's choice.
So you're sort of like imposing a condition that eventually every bid should be included in a box. Or no?
No. So here the thing is, we have infinite block size. We can afford to include all bids. So for the miner, its best strategy is just to include all bids, because it. Sorry.
It's a best strategy.
Yeah, it is a best strategy. Yeah. Thanks. Yeah. Okay, now let's see why this auction satisfies all 3 properties we want. So for UIC, we know from classical mechanism design that it is aimed at like user incentive compatibility. Users does not, overbidding or underbidding does not help the users to increase their utility. Where the user's utility is defined as, if its bid is confirmed, then its utility is its true value minus its payment. And if it's not confirmed, then its utility is just 0. Here, we also want to mention that injecting does not help because in this mechanism, every bit is confirmed independently from other bits. So injecting bit does not help your own bit, say this 2 getting confirmed. So MIC is also kind of easy to see, but still I want to mention the miner's utility. The miner's utility is defined as its revenue minus the payment if it ever tries to inject a bit and that bit gets confirmed. So that part should be distract from the miner's utility. So MIC should also be easy to see because it gains nothing anyway. Okay, so what's interesting is one SCP, when the miner collude with one user, they cannot increase their joint utility. This is because, okay, we know that miner's utility is basically 0 anyway. So the way for them to increase their joint utility is to increase the user's utility. And the user cannot increase its own utility by UIC. And miner can do nothing to help the user here, basically. So we also have one SCP here. Okay, great. Yes.
Doesn't the miner determine R, so the miner could like set R lower? It determines R.
The R is predetermined before the auction starts.
And not by the miner.
Not by the miner. Yeah. If by the miner will just set it to. So yeah, it's predetermined. So okay, great. Now we have posted price auction. We know that it satisfies strict incentive compatibility, assuming infinite block size. But why does it fail for finite block size? So when we have infinite block size, we can't afford to include all bits in the block. However, when we have finite block size, let's say we have block size 2, I can only include 2 bits in the block. So basically, in the first step, I can only put 2 bits on chain. So now, how do we choose these 2 bits? Okay, let's say we randomly select 2 bits that is at least the reserve price for. Okay, so this is a very simple finite block size variant. What can go wrong here? So let's say still this miner user coalition, if we behave honestly, if the miner implements the mechanism honestly, the probability that my friend, this user, being included is 2/3. But why should I do that? Any idea of how the miner can help his friend? Yes.
Take some side payment and get it included.
It just always, yeah, it just always, I would just always include my friend 7, right? If I always include my friend 7, then now the user, the probability of my friend being included is 1. And we know that once it is included, it will be confirmed. So this increased the user's utility and thus increased the joint utility of the whole coalition.
But if you consider the blockchain will roll forever, right? So if we don't include 7 in this block, 7 probably will get included in the next block. So does it really matter that in this case we always try to?
Yeah, so here in this work, we consider one-shot auction. So we only consider one auction where we, like in this specific block, we do not consider what happens in the future. Yeah, I would mention that is another weak incentive compatibility model considered in their previous work.
The blockchain is ever growing ledger that's somehow like infinite blocks.
Sorry, 1 minute. No, so basically here we are just considering that single auction. And if we can, okay, so like considering the block growing forever and consider the potential future cost involved, that model is considered in their previous work. Yes.
We also just think of this model where the values posted are the marginal value being posted like in this transaction versus the next like time when time being updated. It's like users would presumably prefer to have transactions posted now and not later.
I would say so. In this work, we really just focus on this single shot auction. So we are not considering what involves the future cost in the next block. But indeed, that is a very interesting model to consider. Thanks. Okay, so yeah, as previous work showed that no dream mechanism works for finite block size. Basically, as we saw from the example there, because minor implements the inclusion rule, it can choose to help its friend. So to take care of this problem, can we just force an honest inclusion rule by multi-party computation? And that's exactly why MPC helps here. Okay, now let's see how we achieve strict incentive compatibility with MPC assisted model. So in MPC assisted model, we have the mempool here. And now we have the honest majority multi-party computation. You can think of it as a black box that takes into the input of the mempool and outputs the bit to be included. That's specified by the honest inclusion rule. And this MPC can guarantee the correctness of that inclusion.
Why would they choose to have one two?
Just a random example. Because 2 and 1 were never there before, so I just put them there. Sorry if that causes any confusion. I saw a very confused face.
So just choosing 2 random bits.
Yeah. So basically here in this example, I'm just choosing 2 random bits, not 2 random bits, at least the reserve price. So yes.
This minus do honest computation.
Yes. This is guaranteed.
This decision means you can essentially replacing each minor essentially an honest version of it, right? What's the difference between the systemic minor was honest all along?
Yeah, as I mentioned, it's kinds of different. So minor is not honest. They can still deviate here inside the multi-party computation, but
gotcha. So they become honest.
No, they only become honest when you can think of it, they only become honest when implement this inclusion rule, but still I can inject it. And I can tell my friend what to do. I can tell the users, including with me, what you should bid, how you should behave. So it's still different from the classical mechanism design.
Oh, I was asking, could we implement this inclusion rule just like if we had a public source of randomness, like trusted randomness, would that be sufficient to implement the inclusion rule, or do we need multi-party computation?
So I would say the trusted randomness is enough for our example here, where we randomly choose 2 bit, but it is not necessarily the case that all mechanisms use a random inclusion rule. So when there's other inclusion rule, you might need a multi-party computation to do that for you.
What does this assumption mean?
What assumption?
What if there's only one minor? What does this assumption mean? But it's honest majority.
So by honest majority, so by multi-party computation, we are assuming that there is at least 2 minors out there. So we basically have a bunch of minors. They do the computation together for us.
If it's only one minor, then not.
By honest majority there, the minor is honest.
You're saying what's honest about? Sorry, it's. I'm not sure. So
By honest,
they're honestly communicating with the users?
No, by honest, we mean they're not inside the coalition. Any user who are not inside the coalition, we refer them as honest. Yes, I think there's another question.
Oh, that answered the question.
Okay. Yeah. So now with this honest majority multi-party computation, who will honestly implement the inclusion rule for us, we're guaranteed, okay, in the first step, we will choose 2 random bits. So now there's no way for the minor to help its friend anymore. And so we have 1 SCP. Okay, great, yeah.
So how many minors in the coalition? Just 1?
So here we can have like minority number of minors. Let's say I have 100 minors, then I can include with 49 minors. Yes.
What would the counterexample for 2 SCP look like?
We'll get to that.
Okay.
So now great, we have a dream transaction fee mechanism in the multi-party computation assisted model. However, it has some drawbacks. The miner is getting nothing from here. It's zero miner revenue. And the second one is that, as we mentioned, it only works for C equal to 1. So why does it fail when the miner include with 2 users? Let's consider this example where this is our mempool and the miners include with this user with true value 4 and the user with true value 10. And still our reserve price is 4. So here, the thing is that for this 4 user, no matter it is confirmed or not, its utility is always 0. Because 4 is its true value and 4 is exactly the reserve price. So still the joint utility of this coalition is really just the utility of this 10 user. And the probability, if everyone behaved honestly, of it being included was 2/3. So now, if my utility is going to be 0 anyway, why not just self-sacrifice and help my friend? I can choose not to bid. I can choose to abort from the auction, and this will increase the probability of my friend being included. So now if I abort, my 10 user friend is guaranteed to be included, and this increases the probability of it being included and being confirmed, and thus increase the joint utility of this whole coalition. So oops, we don't have 2 SCP here. And actually, it turns out 0 miner revenue and the C equal to 1 is inherent for strict ICE multi-party computation model. So for if we want a dream transaction fee mechanism against a miner user collision with 1 user, the miner revenue has to be 0. And we show that there's no dream transaction fee mechanism even in the multi-party computation model that works for C at least 2. So can we get rid of these 2 drawbacks? And yes, with approximate incentive compatibility. I would say it might not be surprising that it can increase the miner revenue, but it's very interesting that approximate incentive compatibility actually deals with both these 2 drawbacks. Again, the epsilon incentive compatibility allows the strategic players to gain at most epsilon more utility by deviating. And by strategic players, we care about single user, single miner, and miner user coalition. And now we are focusing on miner, including with at least 2 users. Okay, now let's see how this mechanism works. And this is for 2 SCP. So this mechanism is called MPC Assisted Diluted Posted Price. So first, we select all bids that is at least the reserve price as candidates. And then if this candidate is smaller than a predetermined threshold capital T, which is square root of K times M over epsilon, and this M is the presumed upper bound M on user's bid distribution. If the number of candidates is not enough, then we add capital T minus T number of dummy bids. And now we choose random K bids from these T diluted bids to include in the block. And we will confirm those non-dummy bids. Those non-dummy bids then pay the reserve price R, and now miner gets half of epsilon from each confirmed bid instead of getting nothing. So I understand it's hard to parse these equations, so let's take a look at a concrete example. Let's say the upper bound on the user's bid distribution is 10, and we take the reserve price as half of the upper bound, which is 5.
So here the miner gets half epsilon. This number that is related to C being 2, right?
Yes.
Okay, so if C is not 2, then this number
Epsilon over C.
Okay.
Yeah, good catch. And we take epsilon to be 1. Let's say you can gain 1 more utility. Now with this and the fact that the miner include with 2 users, we have the dilution to 4.
So there's no relation between R and epsilon.
No.
So for example, R could be less than epsilon, so we can just create value of nothing.
So so basically you can think of, so epsilon is a parameter into the mechanism and R is an independent parameter. So basically, R and epsilon determines how much we want to dilute to and how much minor gets.
But when people pay less than the minor get, how can it be?
Okay, oh, I see. So here we are, yeah, here I'm assuming that you choose a reserve price R larger than epsilon. And so if R is less than epsilon, then you only get R. Because the miner cannot gain more than what the users pay. So with these parameters, now the protocol looks like this. All bits larger than the reserve price 5, they're selected as candidates. And if the number of candidates is less than 4, we add 4 minus t number of dummy bits. And we choose random k bits from those 4 diluted bits, and miner gains half of epsilon from each confirmed bit. Okay. Let's see why it satisfies 2 SCP. Sure.
Who does who adds the piece and who chooses this random piece?
Multiparty computation among the miners. So you can think of all.
Here there's a bidding model. So one of the miners runs this option, he receives the bids from the players. But then he needs to report those bids to the other miners. What prevents this miner being dishonest, not reported? Or the, I don't know if I understand the model.
So still like user, so okay, this, I think this problem relates to how we instantiate the multiparty computation. So basically you can think of this multiparty computation as a black box for now. And if you're interested in the instantiation detail, we can talk it offline. So this black box takes the whole mempool as input and output what's specified by the inclusion rule. Now let's see why it is 2 SCP. So still for this user, let's say, because now our reserve price is 5, let's say I include with the user with true value 5. Its utility is still going to be 0 anyway. So when there is indeed a dilution, so I only have 3 candidates and we pad a dummy bits into the diluted bits. In this case, even if my friend abort, it is not going to increase the probability of the 10 user being included. However, when there's no dilution, when we have 5 candidates, it indeed can help. When we have 5 candidates, the probability of my friend being confirmed was 2/5. But now if I abort, it becomes half. And the utility of my user increased 1, and that is allowable. So the intuition behind this is that, yes, I can self-sacrifice to help my friend. But when there is a large population outside, the help I can offer is very little. So that is how that is why this dilution helps with 2 SCP. And of course, there's other ways that they can increase their joint utility by no more than epsilon. Let's say the mempool looks like this, where only the 110 user is the only one that bids at least the reserve price. So now if my true value is 4.9, I will want to overbid to the reserve price. So even if I get confirmed, I'll only lose 0.1. But by losing this 0.1, I can bring the miner half epsilon more, which is 0.5 more utility. So by overbidding a single user can indeed, it is possible that a single user can bring the miner no more than half epsilon more utility. And since we have 2 users here together, they bring the whole coalition at most epsilon more utility. And this is how with this diluted posted price, we can achieve 2 SCP. And actually, I want to mention that this auction also achieves asymptotically optimal social welfare. Because let's say we select the reserve price as half of M. If we have a lot of users with large true values, let's say larger than 2/3 M, then we know that there are guaranteed K users that is going to getting beta of M utility. And the miner is getting beta of K epsilon revenue. And so in total, we have beta of KM social welfare, which is asymptotically optimal because K times M is the best you can hope for. Yes?
Basically, I'm not completely understanding. For we're sort of assuming that epsilon is a very small amount in one place and a large amount in another place. Like, we're assuming it's a small amount when it comes to incentivizing the miner to like run the auction at all. But we're also assuming it's a small value when it comes to, we don't care if like cheating can increase your revenue by epsilon.
I would say we still think of it as a small value. It's still small, but okay, miner is now getting something instead of 0, but it's still small indeed.
Okay.
Yeah. So I don't think I have time to talk about the lower bound proof for unscalable social welfare because it's super complicated, but I'm going to give you the statement of what we mean by unscalable and the main technical challenge. So by unscalable would mean that if a transaction fee mechanism satisfies epsilon IC in the plain model, the social welfare is at most beta of epsilon times basically log m over epsilon. Let's just take m to be a large constant. So that means even if the m grows, the social welfare only grows logarithmically, which is very slow, whereas in the diluted posted price, the social welfare grows linearly as m grows. And the main technical challenge for those of you who may be familiar in this area, the main technical challenge is that we cannot even use the famous Myers lemma to do the characterization for approximate incentive compatibility, and we have to build the characterization from scratch. Actually, even if assuming strict UIC, the proof is still very complicated. So I'm just going to show off my slide skill. Yeah. So in conclusion, in this work, we show that with the help of MPC assisted model and by relaxing to approximate incentive compatibility, we can achieve feasibility of a dream transaction fee mechanism, and we can achieve a symptotically optimal social welfare. So this is a full conclusion of the results in our paper. So we show that for strict IC, we can have a dream transaction fee mechanism when c equal to 1, as I show you, and we give a lower bound proof that for C at least 2, there's no non-trivial transaction fee mechanism that can achieve strict IC in the MPC assisted model. And for epsilon IC, we show that there's no universal mechanism that works for all unbounded true values. And we show that if you're willing to assume an upper bound of the bit distribution, you can, we give a construction of the mechanism, but also we give a lower bound showing that in this case, the social welfare must be unscalable. And finally, we give the MPC assisted diluted posted price auction, which assumes an upper bound on the true value and gives optimal social welfare, positive minor revenue against arbitrary C. And this is the results for infinite block size. And I want to comment that here, the minor revenue is also scalable as the upper bound M.
Is this square root of m optimal?
Yes. So there are some open questions remain in this work. So first, so in this work, we're caring about the theoretic feasibility landscape of transaction fee mechanism. So we are directly using a very powerful tool, MPC. But in practice, MPC can be very heavyweight. So it would be nice if we can design practical mechanism with more lightweight crypto tool. And the second one is that in the MPC assisted model, we only give the diluted posted price auction, assuming the upper bound of the bit distribution. It would be interesting if we can design a universal mechanism that works for all distribution. For that is epsilon IC in the MPC assisted model, or if we can rule out the existence of such universal mechanisms. And also there are other interesting problems of decentralized mechanism design. For example, in this work, we are assuming that all slots in the block, they're equal. I don't care about which slot I get. There's no difference between the slots, but it might not be the case in actual blockchain. People might actually care about the ordering of the transactions in the block. So these are more interesting questions to explore in this work, in this field. And actually, little is known in this field. So We do want to see if crypto can help us to get something that is useful. And that completes my talk. Thank you so much.
So going back to the MPC demonstration,
Uh-huh.
so how are you guaranteeing that the input is all of the honest bits?
So first we have the users send their bits to all miners.
Oh, so you're not only sending the bits to one miner.
No, we're sending, yeah, so each user send their bid to all miners, and all miners will reach an agreement on which bids are out there.
Did you consider the complexity in MPC?
No,
Okay, so you are using that block that always out the correct stuff.
so actually the MPC instantiation in our paper is guaranteeing more. So so basically here we are assuming that each user can decide its strategy after the coalition can decide their strategy after observing the mempool. But in our MPC instantiation, we actually guarantee that you have to make your decision independently from the mempool. You have to submit your bid before that, and that is kind of heavyweight. If we don't care, if we are just using MPC for this, everyone can just broadcast send their bids to the miners directly. Any other questions? If no, I guess then that's it. Thank you so much.